Professor will.
Yeah.
Professor, shall we start the session? Yeah. Hello, everyone, and welcome to today's special webinar session on living structure as a new paradigm for maps and mapping in the big data era, organized by the Center of Urban and Regional Planning, known as CURP, at the Institute of Town Planners Sri Lanka, and myself, Chatur De Silva, moderating this session with Dr. Amita Jayasinghe. We both from the Department of Town and Country Planning, University of Monaco. As we all are aware, during the last decade or so, we are witnessing the emerging trends on rich applications of geospatial big data across various disciplines, including humanities, physical science, biology, engineering, business studies, and so on. Now, as town planners and as planning academia, it is important to learn and find ways on how we can use this geospatial big data to improve our understanding of rapidly evolving cities, irrespective of where they are. Ultimately, this understanding can facilitate the decision-making process, commonly known as data-driven decision-making. In that context, the specific objective of today's webinar include to advocate new paradigm for maps and mapping technology, to promote paradigm shift from traditional Euclidean and Cartesian geometries to fractal and living geometries. And the audience today with us are basically the members of Institute of Town Planners Sri Lanka, which includes corporate members and also the student members. With that very brief introduction to the session, let me warmly welcome our speaker today, Dr. Bin Jiang, Professor in Geoinformatics and Computational Geography at University of Gävle in Sweden. Dr. Jiang is the founder and the chair of the International Cartographic Association Commission on Geospatial Analysis and Modeling, and he is affiliated to Royal Institute of Technology, Stockholm, commonly known as KTH, through the KTH Research School at Gävle. He is an associate editor of several international journals, including Computers, Environment, and Urban System, published by Elsevier, and his research interest centered on geospatial analysis of urban structure and dynamics for better understanding cities. He has developed the head-tail breadth, a new classification for data with a heavy tail distribution, which will be one of the topics that he will talk today. And he's a well-known intellectual in the field of urban informatics who shows his research interest in big data analysis and its applications in the real ground. Before I hand over the proceedings to the professor, let me share a few important messages for our participants. First of all, we will listen to the presentation and speech by Dr. Bin Jiang, and then we will move to the Q&A session where we are eagerly waiting to hear your questions, clarifications, and suggestions. And the proceedings of today's webinar will be recorded and later available for your reference. Dear participants, my dear fellow members of the Institute, please keep your microphones muted during the presentation of our speaker to minimize disturbances. And you can use the chat box option for your questions. Alternatively, you may use your hand raise option to show your interest in asking questions, and I sincerely hope that we can accommodate all these questions at the end of the session. With that very brief introduction once again, let me warmly invite Dr. Bin Jiang for his speech on living structure as a new paradigm for maps and mapping in the big data era. Professor Jiang.
Thank you. Thank you very much for nice introduction, Mr. De Silva. And also I want to express my thanks to Dr. Amila Jayasinghe and his colleagues at the Institute of Town Planning, Sri Lanka. It's my great pleasure. So let me to share my research over the past years on maps and mapping surrounding the notion of the living structure, which I have been advocated through the different platforms. So let me share my screen to see if we can make it. screen sharing. Maps and mapping, yes. I have this.
Yeah, we can see the screen,
Yeah.
Professor. Thank you very
Can you
much.
see that?
Yeah, all
Okay,
good.
let me,
Thank you.
yeah, thank you. Let me arrange a little bit better because interface can sometimes cover the okay. Because I'm using only a laptop single screen setting, so it can be a little bit crowded. Okay, ladies and gentlemen, good afternoon from sunny Sweden. Actually, we have several hours time difference. It's now 11 o'clock, just past 11 o'clock morning in Sweden. Yeah, ladies and gentlemen, welcome to this the presentation, and this presentation is intended to advocate and promote living structure as a new paradigm for cartography or for maps and mapping in the big data era. Living structure is a physical phenomenon and a mathematical structure. As a physical phenomenon, it exists pervasively in our surroundings, in buildings, in gardens, in streets, in cities, and in every part of space. As a mathematical structure, it consists of numerous substructures with inherent hierarchy. Across different levels of the hierarchy, there are far more small substructures than larger ones. Yet on each level of the hierarchy, the substructures are more or less similar in size. So in this presentation, I will argue and demonstrate that it is essentially the living structure or the notion, the recurring notion of far more small than largest that makes maps and mapping possible. Living structure should become the core of the cartography and geography and help transform modern cities to become living and more living. How to go to the shift slides? Yeah, okay. Before the presentation, I have a few take-home messages to convey. The first take-home message that I would like to convey is on geometry. What we have learned in high school geometry is largely about the simple Euclidean geometric shapes, which tend to be regular, smooth, and single scale. For example, a square, a triangle, a straight line, and a circle. However, the shapes that are encountered in reality are much more complex and they look irregular, rough, and multi-scales. For example, coastline, a city skyline, and even a tiny ornament. They look irregular, rough, and multi-scales. So the first take-home message that I would like to convey is we must shift our mentality or our way of thinking about the space from Euclidean or Cartesian geometry to fractal and living geometry. The second take-home message that I would love to convey is on statistics. We have learned that many things or phenomena follow so-called normal or Gaussian distribution, named after the German mathematician Gauss. For example, human heights are all around the average 1.75 meters. So this average is also called characteristic height for human beings. If we examine the heights of a larger population, we will find out 50% of people are taller than the average. The other 50% of people are shorter than the average. So 50-50 between the taller and the shorter, very much proportional. However, there are many other things, for example, human wealth, that do not follow normal distribution, but the long tail or heavy tail distribution. named after the Italian economist Planto. Planto discovered that there are 80% poor people, but only 20% rich people in any country. While the normal distribution is widely observed, probably the long tail or heavy tail distribution is far more normal or far more common than the normal distribution. In fact, this long tail or heavy tail distribution underlines the notion of living structure. My research over the past few years is mainly to bridge these two geometries, fractal and living geometries, established by these two masters, the French mathematician Benoit Mandelbrot and Austrian architect Christopher Alexander. In one of the previous slides, I have put these two geometries together in contrast to Euclidean and Cartesian geometries. But the fractal geometry differs also fundamentally from living geometry. For example, fractal geometry is defined under the Cartesian mechanistic worldview. By the way, while the living geometry is established under the Whitehead's organismic worldview. By the way, the Whitehead or Alfred Whitehead is a famous British philosopher who first conceived the organic or organismic worldview. The organic worldview has been taken and substantially developed by Christopher Alexander. He formulated the third view of space. Under the organic worldview, space is neither lifeless nor neutral, but a living structure capable of being more living or less living. Surrounding the notion of living structure, I have developed a series of new concepts, which are all complexly science-oriented, such as nature cities, nature streets, Hatfield bricks, HT index, and scaling law, some of which will be discussed in this presentation. One of the aims of this lecture is to advocate the organic worldview and promote living structure as a new paradigm for maps and mapping in the big data era. And I even go beyond, which I will discuss how, for example, modern cities can be transformed under the notion of living structure to become living or more living. By the way, this year's Nobel Prize in physics is on complexity science about the climate change. So this is a timing lecture in terms of the complexity theory, how it can be applied for understanding maps and mapping. The third take-home message is on maps. The Polish-born American scientist and philosopher Alfred Korzybski, the man who is best known for his fiction, The Map is Not the Territory, has some insightful statement on maps. First of all, a map is not the territory, which means that a map is a representation of the territory. Secondly, a map does not represent all of the territory, which means that no map is one-to-one map scale, and the mapping must be selective. In this regard, I will argue for Hatfield bricks for the selection processing. From the bottom up, so-called the data speaks, and maps for itself. Third, a map has a similar structure to the territory. In this regard, I will argue that the similar structure is living structure, which I intend to advocate and to be the core of the cartography. The fourth statement is that a map is the map of the map of the map of the map, so on, endlessly. This statement sounds very philosophical. However, my primary interest is not on philosophy, but on practice. That is how living structures can be used to guide maps and mapping practice. I will argue that all kinds of the mapping activities, including thematic maps, map generalization, perception of map quality or beauty, and even the cognitive mapping can be conceived as a head-to-bricks processing. I will begin with 3 definitions of the fractal, and in particular, the third definition. A fractal under the third definition is actually living structure. I will try to answer what is living structure and make it clear with 2 paintings. I will present 2 fundamental laws of living structure for understanding Earth's surface as a living structure. Scaling law is characterized by the recurring notion of the far more small than largest, whereas the Tubman's law is commonly referred to as the first law of geography. Everything is related to everything else, but the near things are more related than the distant things. Herewith, I rephrase the first law of geography as the notion of the more similar, in contrast to that of the far more small than largest. In order to better understanding living structure or the scaling law, I will present the head-tail bricks, a new classification scheme I invented for deriving the inherent hierarchy or the underlying living structure of a dataset. Using the famous Robert Duck illusion, I will stress that the perspective and the scope are important for revealing living structure of geographical space. For example, through the perspective of the nature cities and the nature streets. I will argue and demonstrate that mapping is essentially a head-tail bricks. By the mapping, I mean semantic mapping, map generalization, perception of beauty, and cognitive mapping. Finally, I will draw a conclusion by highlighting some key points of this lecture. The very first definition of fractal goes back to 1803, when the German mathematician George Cat developed what is now commonly called the cat set or cat dust. The cat was not the first person who conceived this idea actually, but it was done by someone else, namely Henry Smith, back to 1874. Anyway, take a line of 1 unit, divided it equally into 3 parts, and subtract the middle one with the 2 short lines remaining. The same division and subtraction continues for the remaining lines again, endlessly. Eventually, it would end up with an infinite number of infinite short lines, very much like dust. George Cat is a very religious man, so he thought the largest city of infinite would be God himself. Here with 2 parameters, respectively called scale and the number of lines. On the one hand, the variable scale decreases exponentially from 1, 1/3, 1/9, 1/27, and so on. While on the other hand, the variable number of lines increases exponentially from 1, 2, 8, and so on. Given the 2 exponential variables, one increasing, the other decreasing, they will together form a power law relationship. If we type these 2 variables into an Excel sheet and took logarithm of these 2 variables, we will find out a linear relationship between these 2 logarithm variables with slope 0.63. This 0.63 is called the fractal dimension of cat dust. The Swedish mathematician Van Gogh did a similar thing as George Cat and conceived what is now called curve. Take a line of 1 unit and divide it equally into 3 parts. And the middle one is added a triangle, or the 2 sides of a triangle to be more precise. The division and addition processing continues recursively to form the semi-complicated CURP. Note that unlike the cat set, where the middle part is simply subtracted, while in the CURP, the middle part is added a triangle. Very similar to the cat set, there are 2 parameters behind the CURP: scale and the number of segments. The variable scale decreasing exponentially, 1, 1/3, 1/9, 1/27, and so on, while the variable number of segments increases exponentially, 1, 4, 16, 64, and so on. Again, type these 2 parameters into an Excel sheet and took the logarithm of these 2 parameters. We will find out a linear relationship between these 2 logarithm parameters with slope of 1.26. This 1.26 is called flat dimension of the CURP. I wonder if you have noticed that these 2 examples or their underlying recursive processing is ended up with something very odd. Why? Well, under the Euclidean or Cartesian geometry, everything is measurable, no matter how big or how small, as big as the Earth or the universe, as small as the atom or particles. However, the CURP is infinitely long. How it is possible? Over the 100 years period, mathematicians and scientists have been puzzled by so-called unmeasurable length conundrum. The French mathematician Benoit Mandelbrot was interested in the unmeasurable length conundrum, so-called the coastline paradox, also called. The length of the coastline is dependent on the measuring scale. The shorter the measuring scale, the longer the coastline, or the longer the measuring scale, the shorter the coastline. This unmeasurable length conundrum was also noticed by other scientists, such as Lewis Richardson, who discovered the coastline has different lengths at different scale to map. So puzzled by this conundrum, a group of geographers back to the 1960s at the University of Michigan attempted to solve this conundrum because it was such an important issue for measuring things or objects on maps. And they published a series of research reports. Unfortunately, the conundrum is essentially unsolvable, but it can be effectively dealt with. The problem of the conundrum or the coastline paradox lies not on the measuring scale issue, but the underlying scaling issue. So this, in other words, the difference between scale and scaling. Okay? In his classical paper entitled "How Long is a Coastline of Britain?" Benoit Mandelbrot used flat dimension to characterize the issue of how long is affected by the measuring scale. This is the first contribution to the flat geometry. His second major contribution is to introduce statistics or randomness into the CURP. So we will further discuss in the next slide. Thirdly, he coined the term fractal and established the discipline of the fractal geometry. In terms of the underlying power law or scaling relationship, the first 2 definitions are very similar, but the first definition or the classical fractal is a bit too strict. For example, the scale changes strictly by 1/3, and the number of segments changes also strictly by 4 times. To some extent, the second definition is done by relaxing the first definition by adding a tiny epsilon or delta so that the two parameters are no longer as strict as earlier. This relaxation has some devastation effect and opens up a new horizon for understanding geometry. We can remark that the coil curve module is nearly useless, but the randomized coil curve can be used to model coastline and city skyline. We can make further remark to paraphrase the French artist Henry Smith's exactitude is not truth. It took 100 years to shift from the first to second definition, but it took only 50 years to shift from second to the third. The third definition does not require a power law relationship, but it relaxed from the second definition. The third definition is simply based on the notion or the recurring notion of the far more small than largest. The third definition goes back like this, to quote, a set or pattern is fractal if the notion of the far more small substructures than larger ones recurs at least twice, or with the H index being at least 3. We will come back again to the H index later on. Before that, let's use this simple linear geographic feature to illustrate the third definition. Conventionally, a linear geographic feature is considered to be a collection of more similar line segments. However, it is more correct to consider a linear geographic feature as a set of recursively defined bands with far more small bands than larger ones. The small ones are embedded within the larger ones. In this simple example, there are in total 7 recursively defined bands, x1, x2, and down to x7. The first 3 are larger than the remaining 4. So with the far more small than largest. For the largest 3 in the head, they are also far more small than largest, which means there are 2 small and 1 large. So in the end, the notion of the far more small bands than largest recurs twice with H index 2. So in summary, the third definition has some unique property. It is not based on the power law, but on the notion or recurring notion of far more small than largest. It is relaxed from the second definition. And the fractal, thirdly, the fractal under the first 2 definitions remain the fractal, but under the third definition, it is these 2 non-fractal under the first 2 will remain being fractal under the third definition. The third definition implies that not only coastline, but also highway are fractal, or put it in general, not only nature geographic features, but also human-made geographic features, such as streets, buildings are fractal. If we take the right perspective and scope, of course, for example, a rectangle-shaped building's footprint is not fractal, but it is part of the fractal, a building complex in which there are far more small buildings than larger ones. A street network seen from the perspective of individual junctions and segments is not fractal, but it is fractal seen from individual streets because they are far more short streets than long one, or they are far more less connected streets than the well-connected ones. Now, let's examine why the CURP is fractal under the third definition. See, from the perspective of triangles, there is a recurring notion of the far more small than largest, recurring twice, first 5 triangles out of 21. And secondly, 1 triangle out of 5. So again, with the far more small than largest. The third definition of fractal is actually the definition of living structure. Formally, a living structure consists of many substructures with inherent hierarchy. Across different levels of the hierarchy, there are far more small substructures than larger ones. Yet, on each level of the hierarchy, the substructures are more similar in size. If Mandelbrot set is seen as a living structure, the Julia sets are the substructures. If a Julia set is seen as a living structure, it still consists of many other coherent substructures, so with far more small and largest. By the way, the Mandelbrot set is another major contribution of Mandelbrot. Note that all Julia sets inside the bulbs has a similar structure as the Mandelbrot set, whereas all Julia sets outside of the bulbs have a very similar structure. In essence, there are 2 types of Julia sets. Let me arrange a little bit of picture so I can see. Okay, here is 2 paintings, paintings A and B, which are respectively called composition and the configuration. You probably know that the composition was a painting by the Dutch painter, Pieter Mondriaan, one of the greatest artists of the 20th century. He is famous for his works of art using simple geometric shapes and the primary colors of red, yellow, and blue. Configuration of painting B is modified or revised from painting A, and we can see the slight difference between these 2 paintings on the left stripe. It is a slight difference that makes B is more living or more structurally beautiful than painting A. Why? Well, most people tend to view these 2 paintings as composed of the 7 and the 9 substructures. This view or perspective is very typical and commonly held. I call it the Lego-like assembly view or the mechanic world view. Instead of this static mechanic world view, I took a dynamic, holistic, or organic view. Both paintings are evolved and transformed from the empty square as shown in panels C, D, E. First, from panel C to D, there is a far more new born or newly generated substructures. And again, from panel C to D, there is also far more newborns than older ones. So for the painting A, the notion of the far more newborns than older ones recurs twice, with HD index being 3. So this is the living structure because it meets the minimal condition of being a living structure. However, if we continue from panel E to F, the number of substructures or the notion of the far more newborns than older ones is violated because 6 and 7 is not far more small than largest. 67 are more similar they are. However, from E to G, the number of the substructures changes from 6 to 9. So again, they are far more small or far more newly generated substructures than older ones. So in these connections, that painting B is more living because the notion of far more newborn than older ones occurs 3 times. It is the 3 times and 2 times that makes painting B is more living or more structurally beautiful than painting A. In contrast to painting composition, which represent a living structure that with the lowest degree of livingness, Jackson Pollock's blue pole represents one of the most living structure and the most living in terms of the inheritance hierarchy. It is even more living or more structurally beautiful than the Leonardo da Vinci's Mona Lisa, according to our recent research on structural beauty. By the way, to give a bit background of Jackson Pollock, and he was an American painter and a major figure in the abstract expressionist movement. He is widely known for his portrait paintings. Blue Paul is probably the best among many of his portrait paintings. The painting was purchased by National Gallery of Australia in 1973 and has become one of the most portrait exhibits in the gallery. The painting is now worth 350 million Australian dollars, a 300-fold increase on the $1.3 million when it was first purchased. Having seen these examples of living structure, now let's look at the definition of living structure and or wholeness. Here is definition given by Christopher Alexander. To quote, I propose a view of physical reality which is dominated by existence of this one particular structure, W, the wholeness. In any given region of space, some subregions have high intensity as centers, others have less. Many subregions have weak intensity or none at all. The overall configuration of the nested centers, together with their relative intensity, comprise a single structure. I define this structure as the wholeness of that region, end quote. Note that the center Alexander used here are what I refer to as substructures, which are recursively defined. I define living structure or wholeness that consists of many recursively defined substructures with an inherent hierarchy. Across the hierarchy, there are far more small substructures than larger ones. Yet on each of the hierarchy, the substructures are more similar in size. These two notions, far more small than largest and more similar, underlines the scaling law or living structure. A living structure is therefore to be governed by these two laws. Living structure is a physical phenomenon and the mathematical structure, as we have mentioned earlier. Living structure can be mathematically defined, can be reflected in human mind and heart psychologically. It is a mathematical structure that can evoke a sense of beauty in human mind and heart. Now let's look at these two laws. I formulate the scaling law out of the notion or the recurring notion of the far more small and largest. It is a defect spatial heterogeneity, one of the two spatial properties. They are far more small than the larger one across all scales, ranging from the smallest to the largest. In geographic space or the Earth's surface, or any living structure, the notion of the far more small than largest recurs multiple times rather than just once at different level of scales. Note that it is not more small than largest, but far more small than largest, with far indicating the disproportionate between the smallest and the largest, or between the number of the smallest and the largest. Tubman's law is also commonly called the first law of geography. It is about spatial homogeneity or spatial dependency. Everything is related to everything else, but the near things are more related than distant things. In other words, nearby things tend to be more similar or related. Scaling law and Tubman's law complement each other for characterizing the Earth's surface or any living structure in general. These two laws are basic laws about the two spatial properties, spatial heterogeneity and spatial homogeneity. The scaling law is about interdependency, while the Tubman's law is about dependency. It is important to note that the difference between the spatial dependency and the interdependency. Dependency implies dependent on a local scale, while, for example, my housing price depends on those of my neighbors. However, interdependency implies more complicated and recurring dependency and the global scale, again and again, endlessly. So let me use the fish tag story to elaborate on their difference. If we bought 100 golden fish, all with the same size at the beginning, if one day one fish got a bit big more and eats a bit big, eats little more and get a little bit big, as time goes, there will be effect of the rich get rich and the poor get poor. Among the 100 fish, there will be many small fish, while very few larger ones in the end. So the result of the far more small fish than larger ones came from this interdependency effect through the interaction, communication, trading, and the competition. So the scaling law is also called across all scales, ranging from the smallest to the largest. Scaling is also called scale-free, a long tail. It indicates the disproportionality rather than proportionality. Scaling law implies complexity or non-equilibrium character. The scaling law is universal. Our living structure is pervasive and ubiquitous. In the following few slides, I'm going to present a series of examples of living structure or the notion of the far more small and largest in different settings, in human face, in human body, in space, in society, in galaxy, and even in the universe. A human face is a living structure, so there are far more low attention than high attention. Or the 90% attention focus on the 10% of space of the human face, as shown in this eye tracking fixation points pattern. A human body is a living structure. The count of the living structure recurs at different levels of scale in the brain, in the heart, in the lung, in the neural systems, in many other organs. So here is just an example of the circulatory system. A society is a living structure in which there are far more poor people than rich people, 80% poor people and 20% rich people, characterized by the 80-20 principle. Note that among the 20 rich people, there is still 80-20 partition between the poor and the rich, so on and so forth. A city is a living structure in which there are far more shorter streets than long ones, or far more less connected streets than the well-connected ones. The least connected streets are represented by blue, the most connected by red, and importantly, some in between the least and the most connected, represented by other colors. Again, a city is a living structure in which there are far more low buildings than high ones. In other words, numerous lowest buildings, and very few highest buildings, and some in between the lowest and the highest. Human activity in a city demonstrates the living structure. It implies that 90% of the human activities concentrate on the 10% of space. In other words, in the 90% of space, there are only 10% of human activities, whereas in the 10% of space, there are over 90% of human activities. This is the map showing geolocations of freak photos in Manhattan. Now let's get out of the city scale to the country scale, in which there are far more small cities than larger ones. The city size distribution is commonly characterized by Zipf's law. The largest city is about twice as big as second largest, approximately 3 times as big as third largest, and so on and so forth. At the global scale, the Earth's surface is occupied by far more ocean than land. It is a 70-30 partition rather than 50-50 partition. There are far more small stars than larger ones in a galaxy, and there are far more small galaxies than larger ones in the universe. To better understanding scaling law or living structure, let's look at the head-tail bricks. In this slide, I will do 2 things. First, to demonstrate that head-tail bricks as recursive function for deriving the underlying living structure. And second, to show why one dataset is more living than another. The first dataset consists of 10 numbers, 1, a half, 1/3, and 1/10. The second dataset consists of another 10 numbers, 1, 2, 3, and 10. For the first dataset, the average of the 10 numbers, 0.29, partition the 10 numbers into 2 parts, those larger than the average, called head, 1, 2, 3, and the tail for those smaller than average. So these are far more small than largest. The average of the 3 numbers, 0.2, 0.61, again partition the 3 in the head into 2 parts. The head for those larger than the average, and the tail for those smaller than average. So the first dataset has the recurring notion of far more small than largest with H index 3. However, the second dataset lack of the notion of the far more small than largest. Or in other words, the second dataset violates the scaling law or violate the notion of the far more small than largest. In this connection, we claim that the first dataset is more living than the second. Head-tail bricks has been widely used to various applications, and the method itself has also been extended from head-tail bricks 1.0 to head-tail bricks 2.0. The major difference between these 2 versions lies on the threshold for ending the recursive processing. For the head-tail bricks 1.0, it requires the head percentage must be less than 40% for every iteration. For the second version, the head-tail bricks 2.0, this requirement is relaxed. Instead of every iteration, the 40% threshold for all the iterations on average. In other words, there is no needs to require for every iteration to meet this 40% condition. Living structure represents a paradigm shifting or a profound change in our fundamental thinking about space. The American physicist and philosopher Thomas Kuhn published his classical book, The Structure of Scientific Evolution, back to 1960s, arguing that the path of scientific advance are not smooth, but accompanied by unexpected, abrupt development, very much like stock price change. To the right of the slide, we see a drawing called rabbit or duck illusion. Is it a rabbit or duck? The answer is it depends on your perspective or depends on how you see it. Conventionally, geographical space is commonly considered to be non-living structure, but it's living if we take the right perspective. Seen from the perspective of individual split segments and junctions, a split network is non-living structure. However, seen from individual streets and colored, a split network is a living structure because there are far more short streets than long one, or there are far more less connected streets than the well-connected ones. Note that the streets here are also called named or nature streets, which can be modeled through our software tool, the XWoman. XWoman is a software tool we developed for deriving the underlying living structure for open street networks. It is a freeware based on ArcGIS. It has been widely used for understanding city structure and dynamics. In this website is also a set of the hands-on tutorial on how to conduct the kind of analysis. This is an example of the city of Taipei before and after the XWoman analysis. The street network is a living structure because, as we can see, there are far more short streets than long ones, or far more blue streets than red ones. Here's another example for Stockholm, the capital city of Sweden. Again, far more short streets than long ones. As commonly conceived, a linear geographical features such as a coastline or highway consists of more similar sized line segments. So it is a long living structure, as shown to the left side of the screen. However, seen from the perspective of individual bands, which are recursively defined, there are far more small bands than larger ones. So the linear feature is a living structure. It doesn't matter it is a coastline or a highway. A set of the points is commonly considered as a fragmented, non-living structure. But through the building up a triangulated irregular network and chop the network into many triangles, we will find out that there are far more small triangles than larger ones. Using the head-tail bricks, we will find out that all the small triangles will form what we call nature cities, the red patch, as shown in this slide. Note that the notion of nature cities is defined from the bottom up, unlike the conventional concept of cities that are imposed or defined by government from top down. So such top-down definition of cities make it impossible to compare cities across different countries. Note also that in this illustration, for the purpose, we use a small set of the points, but the nature city are a concept that defined on the big data, usually on the entire country data, if not the entire global data. This slide shows how nature cities are evolved along the time dimension, month by month, using the location-based social media data of Bright Kite, with cities of Chicago, New York, San Francisco, and Los Angeles as examples. This slide shows Chinese cities expanded over the 10 years period between 1992 to 2012, based on the nature city derived from the nighttime imagery and using, again, the head-tail bricks. Here with 2.1 million nature cities of USA generated from 109 million building footprints, all building footprints in the country. The building footprints data was created from satellite image by Microsoft using AI and machine learning techniques. In this slide, we can also see that the nature city matches nearly perfectly with the government-defined city boundaries. To summarize, the Earth's surface is a living structure, and the recurring notion of the far more small and largest at different level of scales, ranging from the global scale, continental scale, to country scale, to city scale, and even to building facade scale, and even down to the ornament. So it is essentially the living structure that makes maps and mapping possible. It is living structure that lies at the core of cartography. And it is living structure that evokes a sense of the beauty of maps in the human mind and heart. So living structure represents a big paradigm shift from Rene Descartes' mechanistic worldview to Alfred Whitehead's organismic worldview. The father of fractal geometry, Benoit Mandelbrot, used to say that Euclidean geometric shapes are cold and dry, a term with a clear sense of the feeling on it. In contrast to the feeling of cold and dry, the term living structure conveys some positive feelings on it. The organic worldview, first conceived by the British philosopher Alfred Whitehead, who extends the mechanics worldview to include the human beings as a part of the world picture. In other words, we human beings are part of the world rather than separated from the world. Under the organic worldview, Alexander developed the third view of space. Space is neither lifeless nor neutral, but a living structure capable of being more living or less living. Under the organismic worldview or the organic view of space, not only Earth's surface, but also the map itself is considered to be a living structure. So under the organismic view of space, mapping can be considered as a head-tail bricks. So in the following few slides, we are going to go through to demonstrate different mapping activities, which can be considered as a head-tail bricks processing. Here with a set of the 1,000 dots whose value follows Zipf's law distribution. It means that the largest value is twice as big as second largest, 3 times as big as third largest, and so on and so forth. Applying head-tail bricks into this data set, we will see there are 4 hierarchy, or there are 4 classes in the data set. For those who are familiar with the nature brick, I encourage you to use the same classification to this data set, you will find out that the result is far less living than the one which shown in the slides. Map generalization can be viewed as head-tail bricks processing as well. A small scale map is essentially the head of the corresponding larger scale map. To paraphrase the Polish mathematician Alfred Korzybski, a map can be viewed as the map of the map of the map, and so on. Another demonstration using Sierpinski carpet and work examples, it is important to note that the generalization patterns of the Sierpinski or the Koikov are strictly adhered to the 3 or 4 specific map skills according to the underlying given structure here. Sorry, I should go to next one. Yes. Here is another example showing how the coastline of Britain was generalized by a head-tail bricks. It is the underlying living structure that tricks the sense of the beauty of maps. Here we see how maps are perceived probably as works of art. To the left of the screen, it is a street network around Stockholm region. Clearly, there are many less connected streets in blue and very few most connected streets in red. And importantly, there are some between the least and the most connected. To the right, we see a settlement pattern in the Chicago region. Clearly, there are far more small settlements than larger ones. We have recently developed the notion of the structure beauty for demonstrating living structure or the degree of beauty of the city plan or images. Let's take a close look at this pair of the city plans. To the left of the screen, it is the city plan for the city of the London. And the 6 colored panels show its 6 hierarchical levels. From them, we can see how it was transformed to become living and more living. To the right of the screen, it is a part of the Manhattan city plan. And the 3 colored panels show its 3 hierarchical levels. In comparison of these 2 city plans, there's little doubt that the city of London is more living or more structurally beautiful. Not only cartographic mapping, but also cognitive mapping or mental maps is essentially governed by the head-tail bricks. Given the underlying living structure, a map can be abstracted as the head of the head of the head, and so on. Those in the top head are landmarks that form the cognitive map, while those in the head constitute small scale maps of different scales. If we show all the nature cities in the UK, it will look like a hairball. By removing those in the tail recursively, step by step, the underlying living structure would be appearing. In other words, the head reflects the whole, or the head is self-similar to the whole. Okay, it is time to wrap up my presentation here with a few points to highlight. Living structure is a physical phenomenon and mathematical structure that consists of the far more small substructure than larger ones. Living structure represents a paradigm shift from Euclidean and Cartesian geometry to fractal and living geometry, from Gaussian statistics to Parisian statistics, and from Cartesian mechanistic worldview to Whitehead's organic worldview. Scaling law or living structure is universal, pervasively existing in our surroundings. mapping as a heterobricks can be applied to all kinds of maps, or mapping activities. A map is the map of the map, and so on. Just as a dataset is the head of the head of the head, and so on. Here is a set of the readings on which this presentation is based. Thank you very much for your kind attention. Any questions and comments are very welcome.
Okay, yes, thank you very much, Professor Jang, for your inspiration presentation. So now we can move to the discussion session. Before that, let me summarize some of the key points highlighted by Professor Jang. Professor Jang is one of the leading scholars in the field of geoinformatics and urban analytics. Okay, so if I relate to his one of the popular quote that is far more small thing than larger ones, he's one of the top scholars. So we can see few top scholars as for his argument also. He published a lot of articles related to the cartography, geoinformatics, and which will be useful for urban planners and decision making related to the space. Okay, so now we can move to the discussion session. But before that, I would like to highlight some of key points. Like, yes, dear participants, like usually the CPD events conducted by ITPSL, and this one might be a little different because we have gone to like theoretical insight rather discussing about the practical issues, specific focus on Sri Lanka. However, so we would like to discuss these concepts and the mathematical models and the new paradigm that Professor Chang introduced for mapping in relate to the planning practice. I think in the discussion session, you can discuss how we can apply this concept into our planning practice. And if you are having different argument or different thought related to the Professor Chang's views, we are welcome and we can discuss, because this is like a learning process. So we all can learn within our discussions. Okay, I think we have about 45 minutes so on for the discussion. So we would like to orderly invite all participants to share your questions as well as comments. And if there is any contradictory arguments via chat box, so then we can take those things in the discussion. So let me highlight a couple of points that introduced by Professor Chen. He promotes the living structure as a new paradigm for cartography, or maps and mapping in the big data era. Because conventionally, like as a planner, we use maps for many purposes, but he introduced new paradigm to highlight the living structure or the wholeness of our space. Okay, that is one of important point where planners can utilize in their practice. And also he introduced the scientific foundation, which can be used for sustainable urban planning and design, especially like quantify or objective to represent the beauty and the wholeness concept. Because in mainly our planning practice, we use a lot of subjective judgment. Yes, those are very good and applicable, but he's introduced some kind of objective scientific foundation to quantify the beauty as well as wholeness based on some mathematical models. Okay, accordingly, the new approach to highlight this the wholeness and like rather thinking individually the geographical features like streets, the buildings, or the rivers and water bodies. So that is one of the important point, because I think we all use this GIS application for our cartographic and some different analysis purpose. In convention approach, we consider this as an individualistic nature based on geometric details, but he argued and proposed new approach where we can use a topological perspective. And also we utilize this head-tail breaks rather using the conventional natural classification. If you're using GIS and so on, you know this natural break and equal interval breaks. So rather than he proposed the head-tail break is a much more useful classification way of highlighting the hierarchies in our space. And also topological representation of space. Just represent your road network or building structure. It is better to highlight the topological hierarchy, which is the highest one or less connected and so on. I think those are very much useful for planning practice. I think in the discussion session, so we can discuss how we can utilize these things in our practice. And also you can argue whether his concept or his ideology, it is applicable or what are the contradictory points. Yes, now we can move to the Q&A session. Dr. Chatura, any questions?
Yeah, thank you very much, Dr. Miller. Professor, we have one question. I'll just take one by one. I think it was sent to the main chat box. The question is, just a moment. First of all, appreciating your presentation. The question is about head and tail brakes. Is it possible to use the head and tail brakes if the first iteration's head percentage is more than 40%? In such situations, can we customize the head tail brakes? If we can customize it, what is the appropriate percentage for head to continue the classification?
Yeah, thank you, dear colleagues. Dr. Joya Sinka made an excellent summary and highlights the key message. For example, the topology, I haven't probably talked much, but yes, he captured. Excellent. Yeah, okay. The first question from the audience on this percentage, 40% threshold. This is an excellent question. Let me share with one story. A couple of years back, when the paper on head-tail bricks paper was just published, one day I received an email from someone from UCL, University College London, a doctoral student, PhD student, said to me that not only heavy tail distribution, long tail distribution, but also normal distribution, he said, can be applied, can be used, can be applied by head-tail bricks. I was very surprised. Then I asked him to send me his data. And then in Excel sheets, I discovered that the normal distribution data, what he meant in email is actually the right scale. So, which means it's not a standard normal distribution, but rather than right scale. So, which means it's still considered as a heavy tail distribution. So back to the question that whether 40% can be relaxed. Yes, it's possible. This is just the 40% is just the ordinal standard. You can, for example, if the first cut you got only, for example, the 50%, then but the subsequent iterations, the percentage is far below than 40%, like 20%, 10%. And then you see, if we keep the first iteration and continue the second, the third, and the fourth, and on average, the percentage of head will be still less than, for example, 40 or even 30%. So that's why we can relax this one to be more sort of flexible. So then we can still get the inherited hierarchy by customize a little bit. So in this respect, I really encourage you, if you are, for example, thinking the research topic, I would love you to carry some experiment to testify different setting. For example, what if we keep the 45%? What if we keep 35%? How the outcome will differ from one to the other. So particularly not only for in terms of how many classes you change, you customize this parameter condition, but also to testify, to verify, to human testify how the pattern generated from different classification method or different parameter setting can evoke a sense of the human feeling, how people perceive this kind of pattern differs when you change the parameter. So this is, of course, open open question for further research. Thank you very much.
Thank you very much, Professor Dr. Amila.
Actually, like as organizing committee, we have reviewed your articles that you have shared previously, and we have dropped some questions. We thought that those questions might be very much useful for participants also to make some kind of discussion. Okay, so I would like to bring this question, like you have highlighted the far more small substructures than large ones. I think, yes, there are a lot of mathematical and theoretical insights go into this argument, but in simply like we can use this concept when it comes to the spatial planning as well as city planning, because like as example, far more small centers than larger ones. Maybe as a planners, we try to make like many centers, but actual sense, like there are a few larger ones and many small centers. Okay, if you take the buildings, it can be Colombo, Sri Lanka, or New York, USA. Maybe the store number of stories might be different, but still like very few high, like tall building or high story building. So can you elaborate this concept, special focus on the cities or the spatial planning and design practice? And I am inviting participants also to share their views, because we have a lot of practitioners. I think they have planned many cities in Sri Lanka as well as regions. So they might come across such a kind of issues when they're planning as well as preparing regulation. I think we can discuss this point further. Yeah.
Thank you, Amila. This is really touched to the bottom line of the living structure, the notion developed by architect Christopher Alexander. He's architect, planner, designer, practitioner designer, actually. The two images you post on the screen indicate the modernist buildings, which favor the larger, not the far more small and largest. Okay, so this is really something that is out of my specialization, but I feel it's really interesting and insightful how to better understanding city planning and even architect design. Not only architecture. Recently, I came across the research in the USA, the baby who was born during the pandemic period, who have their baby's intelligence is less developed compared to a baby who born before the pandemic. So this is a really sent alarming message to the architecture design, urban design, and more importantly, interior design. You know, the space which we live is not just as a shelter, but space has the healing effect. Space can, the good space, what I'm talking about, of course, has a healing effect. Space can nurture, just as we drink water, eat food, our body get nurtured. But a good environment, by good environment, I meant living structure with the far more small and largest, can also nurture our body and nurture our brain development, for particularly for baby who, you know, when baby was born, only their intelligence, only 25% was developed. So very much rely on the environment, what kind of the nurture effect can be bring to the intelligent development for baby. So I think first I want to make sure that that's why the traditional building, not only in Sri Lanka, I mean, across the world, Africa, Asia, American, European, you know, the traditional building that are all with no exception at all with our living structure. But this notion of living structure or non-living structure only was developed after First or Second World War, when, you know, the modern industrial or industrialization have produced this kind of modular production or production line. The traditional things are made are all made, not only buildings, cities, streets, but also artifacts. The painting, traditional painting are all living structures. So this is really, so that's why we have to make a difference between the traditional architect design, which tend to produce living or more living structures, while the industry design, like for example, particularly emerged from the Second World War, the airports, skyscrapers, and the shopping mall, all this kind of the modernist building tend to violate the laws of living structure. The notion of the far more small than largest. So there are also many human tests to test human preference. So here I want to point out, it's not just the human preference, you like or dislike, not so much a personal preference or opinion, but rather than the fact. Also, I would like to point out by fact, I not means that with 100% effect, very much like statistics. The R square value, if we say R square value is 0.7, we tend to say, oh, this is a fact, this is a good correlation. But of course, 70% can be, for example, explained or interpreted by the living structure or underlying statistics, or by the far more small and largest. But we must also leave the certain percentage, 20 or 30% to the human aspect. But we shouldn't shift this to, we shouldn't put the human effect as the first and foremost. But instead, the living structure, the underlying, the notion of the far more small and largest should be the first and foremost effect we have considered when design and or transform cities to be living and or more living. I'm not sure if I have answered your question, Amila.
Yeah, thank you for your detailed explanation. So any thoughts or any comments or from the audience about this concept, far more small substructures than the larger ones? Anyone from the audience like to share their views? So you can raise hand, so then we can unmute your microphone.
Someone just posted a question into the chat window.
Yeah, we have a few questions, Professor. I think one of the questions raised there is probably you address regarding these multiple dimensions of space. Where the question is about the cities as living structures is described based on 2D space. When it comes to 3D space, how we can relate this concept to explain the living structure in 3D representation. Any thoughts on that, Professor?
Basically, it is the same. Of course, in one of the slides, I show the city of London in comparison to Manhattan. But in that slide, I looked at only 2D space. The ground space, so to speak. I didn't look at the vertical. But if you look at the vertical, actually, the Manhattan city is pretty living. Okay, for example, if you look at the vertical direction and the trees and the decorations and city furnitures, and so yeah, basically this notion of living structure can be applied to the 2D, to the 3D, can apply to the city of the country, can apply to the city level, to the street level, to the building level, and even to the room interior part. So that's what I call a series of scales, from smallest to the largest, from horizontal to the vertical. Yeah.
Yeah.
And even beyond the space, as I mentioned, to society, to the people, so and even to the biology. If you look at our organ, our body, they are far more small than largest, right? So this is a really, I feel it's universal, applied to all kinds of settings. Yeah.
Thank you, Professor. And I think we have another question, basically, it's a reflection of the current practice and situation back in Sri Lanka. Let me just highlight the question. Question from Professor Jagat Manasinghe. How would you see it from a land economics point of view? Usually land economists and planners seem to advocate to go for less fragmented and more merged land parcels because of the economics of providing infrastructure and waste of land.
Yes.
Is there a level of optimization in terms of living structure, example 40 to 60 or 30 to 70 head and tail breaks? So what do you respond?
Yeah.
How do you take that question?
Yeah, this is an excellent question, also insightful into the land development. I think this is from the point of view of economics. I mean, nowadays, the city development, architecture design is pretty much dominated, unfortunately, I must say, unfortunately, dominated by how to gather more profit from limited number of the piece of land, okay? And the investor, banking, and the big company, you know, so this is not a good trend. According to what Alexander has been advocating in his entire career, city design, the space, not only, I mean, neighborhood, streets, building, garden, should be by the people, not by architecture, so to speak. Yeah, and architecture tend to be hijacked by this, banking system, by the investors, and who are not interested in produce beauty, but rather than how to gain more profits. So this is really something, particularly in developing country. This is really, for example, in China over the past 20 years, 20, 30 years, the urbanization they created. And according to the Professor Nikos Salingalas, one of the close collaborator of Alexander, who said that in one of his keynote speech, China is not building cities; they are damaging cities. So this is a sort of, unfortunate situation, which is pervasive. I mean, but I think more and more people now realize that this situation. So now the more and more human skill should be produced, because this is exactly what we have been advocating through the notion of the living structure. Yeah, so we shouldn't favor the big lump development, but rather than many small things, emerged not from top down imposed, but rather than individual people, average people, and then we can make space more living and more beautiful. So this is my view.
Thank you very much, Dr. Jiang. I think Professor Jagat himself is one of the experienced planners in the industry. Professor Jagat, any thoughts on the question and the response from Dr. Jiang?
Thank you, Dr. Jiang. Of course, not that I kind of expect a kind of a specific answer for that, but I know that this is the practice. I mean, this is the kind of situation that we can experience anywhere in the world. Whereas the property developers and sometimes the planners, as you said, seem to be kind of advocating this type of behavior. I mean, main thing, as you very correctly mentioned, is insensitivity towards this aesthetics and the kind of beauty of it. Of course, the profit is the kind of thing that drives the kind of the city development nowadays. So it's very important that we look at kind of sensitize these property developers and the planners also towards this these kind of principles of making things beautiful. In fact, in those terms, I believe that this theory that you have brought in is very much effective in that way. Thank you very much for that.
Thank you.
Thank you, Professor. And we have another question. I think this question is more specifically on the process, probably from Samit Madhusanka. Let me state the question. Is there any ability to identify the maturity of cities based on the number of substructures of the particular city? Taking his example, like I did this and got 11 classes for the city of Colombo, which is the main capital city of Sri Lanka, which is a highly urbanized city. But another low urbanized city in Sri Lanka got only 6 classes. So based on that, can we get an idea about maturity level of the city? Any comments, Professor?
Wow, thank you very much. Very good question. This is exactly what we have been researched, and we have a couple of papers will come out pretty soon in the near future. Okay, here this question compare two cities with one have a hierarchy of 11, the other have 6. Okay, this is of course we call the HG index. Okay, so one with HG index 11, the other with HG index 6. But to characterize beauty, we should add another parameter in addition to the hierarchy. Okay, which is a number of substructures. So we call the S. So in other words, the beauty, the formula beauty equal to first the number of subclasses. So more subclasses, the more beautiful. And secondly, the high hierarchy of the substructures, the more beautiful. So if we could multiply these two parameters, the first is the number of subclasses, and the second is the hierarchy or the classes of the substructures. So if we put these two together, then we can nearly determine which one is more living, which one is less. Yeah, and I think Amira has shown this on the screen. This is the two facades. For example, the left one has many substructures, and also not only many substructures, but the high hierarchy. And the right side has a few substructures, and then have few classes. So if we consider these two together, so this also reminded me the question which Dr. Jaya Singh sent me earlier through the email, one of the question about how to judge which one is more living, which one is living. I think this is the same. It has same effect. So we must consider this too. So structure beauty is the multiplication of the number of substructures and the number of the hierarchy, the two facts.
Thank you, Professor, for that illustrative insight that question. Dr. Amila, you have more questions on your end?
Yeah, so I would like to continue the same question or same line of thought. Like as you mentioned, like we can use this concept to compare different cities or different spatial areas to identify which one is more beauty and which one is less beauty. So I have two questions. One is, like, is it possible to compare different size of cities, like mega city with a small village, and then say the small village is much more beauty than mega city? That is first one. Second one, like when we are doing this application, so how to demarcate the boundary of our study area, because yes, we have administrative boundaries. I don't think that is effective boundary to demarcate for this kind of analysis. Okay, so could you please elaborate on these two?
Yeah, thank you. Very good question. Let me begin with the second one. Second one was biggest. You mean the? Sorry, can you repeat it? You mean the compare village to the biggest city, right? Village to the biggest city. And the second one was
the boundary. How we can demarcate the boundary of our study area?
Yes. Okay. Yes. Okay. Let me begin with the second one. Because my research, if you check my paper published, I always take the larger data set, the country level, even global level. And when we decided that the small village or small town or small city, again, we don't use the administrative boundary, because the administrative boundary are not initially not for the purpose of scientific research. The administrative boundary are initially for administrative census purposes. Okay, so that's why we use always use the big data, like whole country, and then we apply head-to-tail bricks to generate the nature city boundary, either nature cities. But remember, this nature city can be recursively defined. So which means within the city, we can also derive nature cities. So city of the city, the city of the city. So these are the nature boundary should be favored for this kind of the comparison in order to have the sort of the objective criteria to be imposed. Not you, because the conventional boundary of either, I mean, cities or provinces tend to be sort of the arbitrary, or at least less objective. So this is my first answer for your second question. And then back to the first one, sure, we can not only compare larger city to a small city in terms of beauty, we can also compare a city beauty to building facade. We can also even compare, for example, in one of our recent work, we compare Jackson Pollock, this portrait painting, to the Mona Lisa. So you see, because we look at the structure, we don't look at on the surface, you know, human or abstract painting. We just look at the structure recursively defined, and then to calculate the degree of beauty, which we call the structure beauty. Of course, this structure beauty wouldn't count all aspects, because they are, of course, we cannot ignore completely the human feeling, the cultures, gender, and the races. There are some effect, but this effect account, remember, maybe the 30%. The 70% effect are counted by the underlying living structure. So yes, of course, we can compare big city to the small city, and even I said that even you can compare city to paintings even. Structurally, again, I'm talking about structure beauty, not the other, I mean, the human related effect. The human related effect cannot be ignored. We are also currently developing some AI technique to integrate the human culture, gender, and the races effect into this kind of characterization of structure beauty. Yeah, thank you.
Yeah, so thank you very much for your answer. From that, I would like to ask another question. Like, so you have mentioned the structural beauty and the perception of human might be different. Like, so have you done any studies to identify the relationship between this structural beauty that can be calculated based on your mathematical model and actual human perception on this beauty? Have you done any research or
We are, you know, there is a problem, you know, if you Google, it's called 3M, you know, 3M company has a software, it's called, what is called? VAS, Visual Attention Software. It's called a visual attention. If you Google visual attention software, it's software, of course, you have to pay small money, and then the software is using AI machine learning technique to mimic how human eyes capture, you know, the movement, eye movement. But it's not based on the eye movement devices, but instead of using computer algorithm to mimic the eye tracking devices result. So this VAS software can capture human attention while you're watching image on your screen. And then after that, it produces a heat map, which one is most heat, with high attention, which one has a low attention. So this kind of the technique based on the biometrics data of human beings can be used to capture the human aspect about the perception of beauty. And then this kind of result based on the matrix data can be compared to the structure beauty, which we calculated. We see pretty much, according to our rough, not a detailed scientific research, but we are going to investigate this into detail in the future. But for now, we really conclude that what we calculated based on the living structure matches very well to the human perception and cognition. But of course, for sure, there's some difference, there's some deviation. So this is the deviation is something which we want to integrate together. So in other words, structure aspect, the human aspect can be, integrated to improve, to enhance our understanding of human perception on beauty. Yeah, thank you.
Yeah, I think it might be a good research areas for our young researchers in Sri Lanka also to study the relationship between structure, beauty, and human perception. Yeah, Dr. Chatura.
Yeah, I think.
Let me jump in before next question. I really encourage young students to compare, particularly Sri Lanka has very rich architecture, traditional, very rich, not only, architecture, city planner, but also the painting artifacts, and compared to the modern ones, and to see, even conduct human test without, advanced technique, eye tracking devices, just simply ask people, ordinary people on the street, and to verify which one they prefer. So actually the difference between this traditional one and the modernist one is very much, very much sharp, not just so blur, so fuzzy, but it's very much, I would usually conclude that the 70% favor the traditional one, while only 20 and 30 favor the modernist ones. Yeah. Okay. Yeah. Go ahead.
Yeah. Thank you very much, Dr. Chiang, on that. I think I also was about to ask that question on behalf of the young. Most of them are young planners who present here, who sort of seeking out their future career, future academic pathways. So maybe some of the suggestions are very, very useful. Maybe we have time for another 2 more questions, and we have another question coming up in the chat box from Professor Jagat Manasinghe. Let me just quote the question. Do you see this explanation of beauty as a function of number of classes and hierarchy as a universal phenomena, or can there be differences unique to different cultures? Example, some cultures see having more number of classes is more beautiful, example Indian, and another see as less classes as beautiful, example the modern movement products. So how do you comment on that, Professor Yang?
Yes, we have somehow touched this question in the early discussion. Again, I think I quite open-minded to encourage young students and researchers to put this question into your, scientific investigation. Yeah, my conclusion, or based on my reading of the Alexander, there is a shared notion of the beauty among the people, and even among the different peoples. But when we see this is shared, we never claim 100% or 90% or 95%. We claim that at least 65 or 70% of people share the certain, which is in line with what we calculated. So in other words, the structure beauty only account for the 70% of effect of the beauty. We have to leave the 30% to, to human aspect, and we said, culture difference, gender, and cross countries, for example. Yeah. So again, these are, scientific investigation to do, but my belief, and also based on the literature, that the most people tend to have sort of the agreement on what is beauty or what is beauty, but we cannot deny the certain arbitrary feeling, and particularly people, for example, who have been brainwashed by modernism or post-modernism movement. So this is something, which we want to. So this is also, I think, make this discussion interesting. Is, we are open-minded. We can investigate to see if there's a contradictory between the human perception and the structure beauty. Yeah. So this is my.
I think
Yeah,
that
in my view.
comment basically sort of reflect on unlimited opportunities available for young researchers to sort of raise their hand and say, I'm going to explore it. So,
Yes.
Professor, I think another question I would like to raise. Maybe we had a kind of informal discussion at the beginning on the same thing. That what is your advice and suggestions for young researchers and young planners who really have sort of a interest in further studies on this? On any suggestions on that, probably?
2 or 3 years ago, together with some colleagues and collaborator of Chris Alexander, we developed a master diploma program called Building Beauty. Building Beauty. If you type buildingbeauty.org, you find that in Italy, we developed that master's architecture school completely inspired by Alexander. Actually, Alexander and his wife, Maggie Alexander, together with some former students of Alexander and the colleagues of Alexander, we created this. Maybe I can type here. It's called the Building Beauty in Building Beauty.org. If we go to the website, one word without a space in between. So Building Beauty, one word.org. You'll find the detail of this program. You know, if you have finished the 3 year or 4 years a bachelor degree, and if you want to thinking the further training or education, and along this line of what we discussed on living structure, this is probably the option which you can go through. And of course, in my school, we have 3 or 4 master program. We want to welcome young students to join us, you know, and or as exchange students come to us. And over the past years, we have received many students from Taiwan, China, and many even from European countries through the Erasmus program. So this are, I mean, what I can, of course, my personal research project. We also welcome young research if we have some PhD opportunity in the future. So I'm very much looking forward. Yeah.
Thank you, Professor. I think that must be encouraging information for our young researchers. Dr. Amila?
Yeah, I think now almost we are at 4:30. So I think this may be the last question. Like I would like to focus this question about this big data era, because in the webinar topic also is about the big data era. So can you suggest so what are the opportunities available for spatial planners or the spatial decision makers in the era of big data? Especially I study about space and analyze the spatial relationships. So what are the new opportunities and new areas we get? So yeah.
Because I just finished one proposal last week about the big data, how to produce particularly open access, not government data. The government, I always said in my paper, in my writings, the government data is not big data, no matter how big it is. You know, it's not the bigness. Big data is not about the bigness. Of course, government has a power, has authority to gather data, but the government data has not big because the time stamp is too rough. So the data gathered through the census every 10 years, every 5 years, okay? And data gathered about the traffic, about transportation, maybe monthly, yearly, certainly not weekly, not daily, not minutes, not hourly, right? So the big data, what I meant, I often refer to like a tree data, social media, location-based social media data. You know, so it has a GPS location, a couple of meters resolution, and in the time scale, it's up to minutes to seconds. So this is really the big data. So big data, I said, is a new paradigm which can be utilized to derive the underlying living structure, we cannot use government data to derive underlying living structure. Of course, satellite image, particularly nighttime image, pixel, then we can derive underlying living structure. Okay, so back to the city planning. First of all, we must rely on big data to diagnose the space, to diagnose cities or neighborhood, how living or how less living. And afterwards, we propose how to heal it, how to transform it to be living or more living. If it's less living, we try to make it living. If it's already living, we try to make it more living. So this is, this is really, the right time in this big data era. And the data which emerged from the internet, from the social media, can be used to study, to diagnose the space and the cities. And then afterwards, after the diagnosis, then we can propose how to improve the recurring notion of the far more small and largest to make it more living or more beautiful. Thank you.
Thank you very much, Professor Jiang. I think it must be a very informative and inspiring Saturday evening for all young folks join, and also not only young folks, but also all our planning community joined from Sri Lanka. Thank you very much, Professor Jiang, for wonderful presentation and also for taking up the questions. And as the moderator of the session, we also thank our participants for sort of interacting and making it a kind of a vibrant session. So thank you very much, Professor Jiang, and also our participants. And let me sort of hand over the proceedings back to our organizers, the CURP, Center for Urban and Regional Planning at the Institute of Town Planners Sri Lanka. So the director, Mr. Lana Tarendu Abejiva, to deliver the formal vote of thanks. Thank you very much.
Thank you.
Thank you, Dr. Chatura. Am I audible?
Yes.
Yes, thank you.
Yeah.
Good evening, everyone. And it's my pleasure to deliver the final remarks of the webinar on behalf of the Institute of Town Planners. First of all, we extend our most sincere gratitude to Professor Bing Jiang, the resource person of the day. Thank you very much, Professor, for your wonderful session and sharing your knowledge, experience with the participants. Wish you all the best for your future endeavor. And secondly, a big thank to Dr. Amila Jayasinghe and Dr. Chatura De Silva for their support in moderating this technical session and giving their fullest support for coordinating the event in different manner in this webinar. Thirdly, I want to thank the Executive Council of the ITPSL, the Institute of Town Planners, for their guidance and directions, and also the Professional Affairs Board of the Institute, same with their directions. And finally, I want to thank all the members who participate for the webinar and their involvement in asking questions and everything for the active participation throughout the session. Hope very best for all of you, and thanks for joining the webinar, and have a nice weekend. See you soon.
Thank you. Thank you very much. Thank you again to my Sri Lanka colleagues and invitation for this webinar. Very interesting. I have learned also a lot from the discussion. And this seminar is out of my research interests, but also out of the ICA commission, ICA working group, which I have been organizing, under the umbrella of International Cartographic Association. The new established a working group on digital transformation of the National Map Agency. So for those who are interested in this topic, you can just come to my website to discover this ICA working group activity. Thank you very much. Have a nice weekend for all, everyone.
Thank you.
Thank you very much. Have a nice weekend.
Thank you.
Thank you.
Bye-bye. Bye.